Welcome back to ByteLearn. In this video, we cover hashing, one of the most widely used ideas in all of computer science and one of the most misunderstood topics in system design interviews. Hashing is not just a data structure, it is a mechanism that shows up in distributed caches, database sharding, URL shorteners, password storage, and content deduplication. Every one of those systems uses hashing for the same underlying reason. This video makes that reason clear. Instagram stores over 100 million photos every single day across their entire history, that is tens of billions of images. If a user uploads a photo that already exists, the same Bollywood movie poster uploaded 10,000 times. Instagram needs to detect that duplicate. Without hashing, you compare the new image against every existing one, O of n, unworkable at scale. With hashing, you compute a hash of the image content and do a single lookup O of 1. Regardless of how many images exist, that gap between O of n and O of 1 is why hashing is one of the most important tools in a system designer's toolkit. Hashing is not a single thing, it is a pattern that shows up in 5 distinct system design contexts. Distributed caches use it to route keys to nodes. Database sharding uses it to route user requests to the correct shard. URL shorteners use it to generate shortcodes from long URLs. Password systems use it to store credentials without ever storing the actual password. And content pipelines use it to detect duplicates. Every one of these applications uses a hash function, but for different reasons with different properties required. This video covers all 5 and gives you the framework to pick the right approach in any interview. In this video, we start with the properties a good hash function must have and why each property matters. We trace how hash tables achieve O of 1 lookup. We compare the two approaches to collision handling, chaining, and open addressing with concrete trade-offs. We then walk through 5 real-world system design applications of hashing with animated diagrams. We cover what breaks at scale and finish with a 4-question interview framework. This video is for 2 people. If you are a software engineer who has used hash maps and Redis without thinking deeply about what is underneath, this video shows you the mechanics and connects them to the system design decisions you make every day. And if you are preparing for system design interviews, every question that involves a cache, a shard, or a distributed lookup requires you to reason about hashing. This is the foundation. Stay till the end. We are going to show you the failure mode that makes naive hashing unusable in distributed systems, why adding a single new server can invalidate every cached key and redirect every database query. That failure is not just interesting, it is the exact reason consistent hashing was invented. Understanding the failure first makes episode 6 on consistent hashing click immediately. One prerequisite: if you have not watched the client server architecture episode in this series, watch that first. We reference load balancers and distributed databases and assume you know what they are. Everything else in this video, we build from first principles. Let us start with the hash function itself. The fundamental problem hashing solves is lookup speed. If you have a list of records and you want to find one, the naive approach is to scan from the beginning until you find it. Linear time for 1,000 records, that is fine. For 50 billion records, the scale at which systems like Instagram or Aadhaar operate, linear scan is unusable. Hashing turns that scan into a single computation. You calculate the hash of your key, use that hash as an array index, and go directly to the location of your data. One computation regardless of total size. The core idea is simple enough to state in one sentence. A hash function takes any input and produces a fixed size output deterministically. Same input, always same output. That property, determinism, is the entire mechanism. If you hash Rajesh today and get index 42, you will still get index 42 next week. So when you want to store something, you hash the key to find where to put it. When you want to retrieve it, you hash the key again to find where it went. No scan, no search, one step. Before we go into the mechanics, let us map where hashing appears in system design, because the 5 applications all look different on the surface, but use the same underlying idea. Distributed caches use hashing to route each key to a specific cache node. Database sharding uses hashing to route each user ID to a specific shard. URL shorteners use hashing to generate shortcodes from long URLs. Deduplication pipelines use hashing to detect identical content without byte by byte comparison. And password systems use a one-way hash to store credentials safely. 5 applications, 1 mechanism. Let us understand the mechanism first. The first property, determinism. Hash of Rajesh must always return the same value every time on every machine. This is not obvious. A function that returned a random number would technically map inputs to outputs, but it would be useless for retrieval. Determinism is what makes lookups possible. Without it, you cannot find what you stored. The second property, uniform distribution. A good hash function spreads outputs evenly across the available range. If your hash table has 1000 buckets, a good hash function sends roughly the same number of keys to each bucket. A bad hash function clusters everything in bucket 0. Uneven distribution creates hotspots. Some buckets overflow, most are empty. The entire point of hashing is defeated. The third property, speed. The hash function itself must be fast, constant time. If hashing a 1 GB file takes 10 seconds, you have eliminated the O of one lookup but introduced a 10-second computation. For deduplication of large files, this matters, which is why SHA-256 is optimized for hardware acceleration. For small keys like user IDs or strings, speed is rarely an issue, but it is still a design requirement. The fourth property, the avalanche effect. Change one bit of the input and the output should change by roughly half its bits. Hash of Rajesh and hash of Rajesh, one character difference should produce completely different outputs. This prevents patterns in inputs from creating patterns in hash values. It is especially critical for security uses. An attacker who can see your hash should not be able to infer anything about nearby inputs. The fifth property applies to cryptographic hashes. The function must be one way. Given the hash of a password, you cannot reverse engineer the password. This is what makes bcrypt safe for password storage. The database stores the hash. Even if the database is stolen, the attacker cannot recover the original passwords. They would have to try every possible input until they find one that produces the same hash. This is called a pre-image attack, and good cryptographic hash functions make it computationally infeasible. Not every use case needs every property. For database sharding or cache routing, you need determinism, uniform distribution, and speed. But you do not need one-way or cryptographic strength. Murmur hash and XX hash are fast, well-distributed, and non-cryptographic, perfect for this. For password storage, you need one-way and resistance to brute force, bcrypt or Argon 2, which are deliberately slow to make brute force attacks expensive. For content deduplication, you need collision resistance. SHA-256 gives you 2 to the power of 256 possible outputs, making accidental collisions essentially impossible. Use the right tool for the job. A hash table is built from two components, an array of fixed size n and a hash function. The array is called the bucket array. Each slot in the array is called a bucket. Let us trace a lookup from key to bucket. A key arrives, say user ID 121245. The goal is to store or retrieve the value associated with this key in the fastest possible way. The key is passed to the hash function, say murmur hash. Murmur hash computes a large integer 0x9f82c4b1 in this example, and we take it modulo the array size. If the array has handed 24 buckets, 0x9f82c4b1 modulo 1024 gives index 433. The hash function ran in constant time. The index is determined. The system accesses bucket 433 directly, a single array index operation O of 1. It does not scan 0 through 432. It does not binary search. It goes directly to position 433 in memory. If the key value pair is there, it is returned. If the slot is empty, the key does not exist. This is the entire mechanism. Now a problem. A second key, user ID 78901, also hashes to index 433 after modulo two different keys, same bucket. This is a collision. Collisions are mathematically inevitable once you map a large key space into a smaller array. The hash function cannot avoid them. What matters is how the system handles them. The most common resolution chaining. Each bucket holds not a single value but a linked list. When a collision occurs, the new key value pair is appended to the list at that bucket. Lookup follows the list until the correct key is found. With a well distributed hash function and low load factor, most chains stay at length 1 and performance stays close to O of 1 on average. The lookup is complete. The value is returned to the caller from key arrival to value retrieval, one hash computation, one array index access, one chain traversal at most, O of 1 average time regardless of how many total entries the hash table holds. This is why every language runtime, Java hashmap, Python dict, Go map, is built on exactly this mechanism. The load factor is the ratio of stored entries to total buckets. When it exceeds about boil 75, meaning 3 quarters of buckets are occupied, collision probability rises sharply and performance degrades. The solution is rehashing, creating a new larger array and reinserting every existing entry by recomputing hashes. Java's hashmap, Python's dict, and Redis all implement automatic rehashing. It is a one-time O of n operation that restores O of 1 average performance. The two approaches handle collisions fundamentally differently. Chaining stores colliding entries in a linked list hanging off the bucket. The array points to a chain. Open addressing stores everything inside the array itself on collision. It searches for the next empty slot by probing forward. Memory behavior differs sharply. Chaining allocates linked list nodes on the heap for each collision. Extra memory per entry, scattered across memory. Open addressing stores everything in the fixed array. No extra allocations. And because the data is contiguous, it is CPU cache friendly. In practice, open addressing has better cache performance for small key value pairs. Under load, they behave differently. Chaining degrades gracefully, longer chains, but each lookup still traverses only one chain. Open addressing degrades sharply above a 0.7 load factor due to clustering, a probe sequence that finds occupied slots repeatedly, wasting comparisons. Open addressing must be resized earlier and more aggressively. Deletion is where open addressing gets complicated. In chaining, deleting an entry is a simple linked list removal. In open addressing, if you simply clear a deleted slot, future probe sequences that pass through that slot will break. Lookups will stop too early and incorrectly conclude a key does not exist. Deleted slots must be marked as tombstones, which accumulate and need periodic cleanup. Choose chaining when entries are large objects or when load factor is unpredictable. Most general purpose language runtimes use chaining for exactly this reason. Java's hatchmap and Python's dict both use chaining. Choose open addressing when entries are small and fixed size and cache efficiency matters. Database index structures and high performance hash maps for embedded or real time systems often prefer it. Modern variants like Robinhood hashing reduce the worst case performance of open addressing significantly. Let us see hashing applied to a real system design problem. Database sharding. The database is too large for one machine, so it is split across 3 shards. The routing rule is simple: hash the user ID and take modulo 3. The result 0, 1 or 2 determines which shard handles that user's data. Let us trace two requests. User 11345 sends a request. The hash router receives it. The hash router computes murmur hash of 12345 modulo 3 equals 0. This request goes to shard A. The request lands on shard A. Because the hash function is deterministic, every future request for user 12345 will also land on shard A. User data is always co-located. Joins, history, preferences, all on the same machine. No cross-shard queries needed. Shard A processes the query and returns the result to the client. The response travels back along the same path. A different user 6789D0 sends a request. hash of 67890 modulo 3 equals 2. This user goes to shard C. Different user, different shard. Deterministically, the two users never share a shard, and no lookup is needed to know which shard to use. Shard C handles user 6008 notice shard B in the middle is idle in this trace. This highlights the distribution risk of naive hash sharding. If user IDs are not uniformly distributed or if some users generate far more traffic than others, shards end up with unequal load. This is why choosing the right hash key matters as much as choosing the right hash function. Shard C returns the result for user 67890, two users, two shards, zero cross-shard coordination. Each routing decision required exactly one hash computation. The key guarantee hash sharding provides. Routing decisions require no external lookup, no directory service, no metadata query, no coordination. The hash router computes the shard index on the fly from the user ID alone. This is O of 1 routing at any scale. It is why hash-based sharding is the default approach for distributing user data across database nodes. Let us trace hashing through a complete URL shortener pipeline, the same architecture bit.ly, razor-page short links, and most link shorteners use. A user submits a long URL to the shortener API. The request hits the load balancer. The shortener service computes SHA-256 of the long URL, producing a 64-character hex string. It takes the first 7 characters and encodes them in base 62 using letters and numbers, no special characters. 7 base 62 characters give 62 to the power of 7 possible codes, about 3.5 trillion combinations. Enough for any link shortener. The generated short code, say XK9MQ3P, is checked against the database. It is theoretically possible that two different long URLs produce the same first 7 SHA-256 characters, a collision at the truncation step. If the short code already exists in the database pointing to a different long URL, the service takes the next 7 characters of the SHA-256 hash and tries again. If no collision, the mapping is stored. First in Redis keyed by the short code with a long TTL because most redirects happen immediately after creation and cache hit rate is very high for fresh links, then persisted to the database for durability. The short URL is returned. From this point, any click on bit.ly xk9mq3p triggers a reverse lookup. The short code is looked up in Redis first, then the database on a cache miss, and the user is redirected to the long URL. One hash computation at creation time. O of 1 lookup on every redirect. This is hashing powering a production system at scale. A bonus property, if the same long URL is submitted twice, SHA-256 is deterministic. It produces the same hash. The first 7 characters are the same. The lookup finds the existing mapping. The same short code is returned without creating a duplicate entry. Content deduplication falls out naturally from hash determinism. No explicit duplicate check needed. The first failure mode, hotspots. Hash functions produce uniform distribution when keys are themselves uniformly distributed. But real-world keys often are not. If most of your users have IDs in a narrow range, or if one user generates 1,000 times more traffic than others, even a good hash function routes an unfair share of work to one shard. That shard becomes the bottleneck. The other shards sit mostly idle. This is called a hot partition, and it is one of the most common production incidents in distributed databases. The second failure mode, and the most dangerous for distributed systems. Suppose you have 3 database shards and you add a fourth. Your routing rule was hash modulo 3. Now it is hash modulo 4. For most user IDs, modulo 3 and modulo 4 produce different results. Roughly 75% of all your keys now route to the wrong shard. Every cached entry is invalid. Every database query routes incorrectly until data is migrated. In a live production system, this can mean hours of incorrect reads and writes during shard migration. This is the fundamental weakness of naive modulo hashing. And it is exactly the problem consistent hashing solves, which is episode 6. The third failure mode, the birthday problem. How many people need to be in a room before there is a 50% chance two of them share a birthday? Not wait 183. The answer is just 23. The same unintuitive mathematics applies to hash collisions. In a hash table with n buckets, you start seeing a 50% collision probability after inserting only the square root of n entries. Not n entries. For a table with a million buckets, significant collisions begin around 1,000 entries. This is why the load factor threshold of 0.75 is a hard engineering rule, not a guideline. The fourth failure mode, using the wrong hash function for the job. MD5 is fast but cryptographically broken. It should never be used for password storage. SHA-256 is cryptographically strong but relatively slow for operations that run millions of times per second, like cache routing. Bcrypt is deliberately slow, ideal for passwords, completely wrong for database sharding. The right tool for the right job. Murmur hash or XX hash for high throughput routing, SHA-256 for content deduplication, Bcrypt or Argon2 for passwords. Hashing related questions come in many forms in system design interviews. How would you shard a user database? How does your distributed cache decide which node stores a key? How does your deduplication pipeline detect identical uploads? The answer always starts with four questions. First question, what are you hashing? And is that value uniformly distributed? User IDs work well if they are sequential or random across a wide range. Timestamps work poorly as shard keys. All writes in a given second go to the same shard. Geographic codes cluster by region. Pick a key that distributes your workload evenly, or you will build hotspots in from the start. Second question, do you need security? For sharding and cache routing, the answer is almost always no. Use murmur hash or XX hash, fast, well distributed, non cryptographic. For content deduplication where you need collision resistance, use SHA-256. For password storage, use Bcrypt or Argon2, deliberately slow with built-in salt. Never use SHA-256 for passwords, it is too fast, which makes brute force attacks cheap. Third question, and the one that separates junior from senior answers. Uneven modulo hashing breaks when topology changes. If you add a fourth shard to a 3-shard cluster, 75% of keys remap. If you are designing a caching layer or a shard scheme that might scale, naive hashing is not the answer. The answer is consistent hashing, which limits remapping to 1 over n of keys when one node is added or removed. That is episode 6. Fourth question, how do you manage growth? For in-memory hash tables, the language runtime handles rehashing automatically. For distributed sharding, rehashing means data migration, a planned engineering operation. Define your maximum load factor threshold, build automated monitoring for it, and design the migration process before you need it. Discovering you need to reshard during a production incident is the worst time to design the process. The answer that distinguishes you in any system design interview. Structure your response around these four questions. Justify your key choice with distribution reasoning. Match your hash function to the security requirements. Acknowledge the scaling failure of naive modular hashing and name consistent hashing as the solution. And define your load factor management strategy. This shows you understand hashing not as a data structure trick, but as a distributed systems design decision. Before hash tables and cryptographic hash functions were applied at the infrastructure level, every one of these operations was either slow or unsafe. Database lookups required full table scans before indexes were standardized. Caching was inefficient without a fast way to route keys to nodes. Deduplication required byte by byte file comparison. And password storage in plain text or reversible encryption meant every data breach was catastrophic, every credential exposed. Hash functions at scale changed each of these. Aadhaar is the largest biometric identity system in the world, 1.4 billion enrolled residents. When a new person enrolls, the system must verify they are not already registered under a different identity. A perceptual hash of their fingerprint and iris scan is compared against the hash index of all existing records. Without hashing, Comparing against 1.4 billion records sequentially would take hours. With the well-indexed hash structure, it completes in seconds. This is hashing enabling a national scale identity infrastructure. Content deduplication at internet scale only works because of hashing. YouTube receives 500 hours of video every minute and must detect re-uploads. The same Bollywood film uploaded from different accounts. SHA-256 fingerprinting gives every video a fixed size identifier. Two identical files have identical hashes. Two different files almost certainly have different hashes. Git uses SHA-256 to identify every file and commit. The entire version control system is a content addressed hash store. BitTorrent uses SHA-1 to verify every downloaded chunk. Without the hash, you could not trust that what you downloaded is what was shared. These are not edge cases. Hashing is foundational infrastructure. Password storage is a story of hash function evolution driven by attack capability improvements. In the 1990s, MD5 seemed like a good idea. It is a one-way hash, so you cannot reverse it. But it is so fast that a modern GPU can compute billions of MD5 hashes per second. An attacker with a stolen database can try every common password in minutes. The solution was to make the hash function deliberately slow. Bcrypt and Argon 2 are designed to take around 100 milliseconds per computation on modern hardware. An attacker checking a billion password guesses would need 100 million seconds, over 3 years per account. The right hash function turned a catastrophic breach into an acceptable one. Hashing is one of those ideas that seems simple on the surface. Compute a function, get an index, and reveals increasing depth the further you go. O of one lookup that works the same at 100 records or 100 billion, sharding that routes queries without any directory lookup, deduplication that detects identical content in milliseconds regardless of file size, password storage that makes stolen databases worthless. One mechanism powering all of it trillions of times every day. Now you understand how. That is hashing from the 5 properties of a good hash function through collision handling to 5 real-world system design applications to the 3 failure modes that matter at scale. You now understand not just what hashing is, but when to use, which kind of hash function, and what breaks when you scale naive hashing beyond a single machine. Here is exactly what you can now do. Explain why hash tables give O of one lookup and what the load factor limit means. Pick the right hash function for each use case. Fast, non-cryptographic for sharding. Collision resistant for deduplication. Deliberately slow for passwords. Design a hash-based sharding scheme and identify its failure modes. And when someone asks how you would scale beyond naive modulo hashing, you can name consistent hashing and explain exactly why it is needed. Next video, consistent hashing. You now know exactly why naive modulo hashing breaks when you add or remove a shard. Episode 6 shows you the solution, the ring-based consistent hashing algorithm that limits remapping to 1 over n keys on any topology change, and the virtual node technique that fixes uneven distribution. It is the direct follow on to what you learned here. Link is in the description. Subscribe to ByteLearn for one system design concept per week, explained through animated diagrams, connected to real Indian tech systems. Interview ready. Hit the bell. Episode 6 drops next Wednesday. One question before you go. Which application of hashing surprised you most? That Aadhaar uses hash-based biometric deduplication at 1.4 billion records. That Git is essentially a content-addressed hash store. That Bcrypt is deliberately slow to make brute force attacks infeasible. Or the birthday problem math showing collisions happen far sooner than intuition suggests. Drop it in the comments. It tells me which parts to go deeper on in future videos.